let me start by first telling you that we are studying simple harmonic motion. And each one of these words is kind of there for a reason. Whether I say simple harmonic motion or simple harmonic oscillations, I'm trying to say the same thing. So in that phrasing, each of these words actually has specific meaning. Oscillations are any pattern of movement that is the same all the time. Any pattern of movement. So I can really end it by just saying that. A pattern suggests that it's doing something repetitive or the same all the time. Harmonic means that it's repeated in a regular way. The timing of it is regular. So when we combine harmonic oscillator or harmonic motion, we mean that our object is going back and forth or through a path that is repeated in regular intervals of time. But the word simple here has very specific meaning. Simple means that the motion can be modeled with a sine or a cosine function. Now, I needed to do this in first period, and I got the answer I wanted, but let me make sure. Raise your hand if this looks familiar to you, and you know what it is, and you know what the graph would look like, and you would know how to measure these values from the graph. Just curious. If it's important, if you don't know, that you not fake it, because then I can assume you can do it. So if you do know, great. If you don't, fine. This is normally taught during pre-calc, and normally it's taught in about the next month. So you guys are doing trig identities, I believe, in pre-calc. The next thing you will do are trig functions. This is a trig function. And each part of this function, the A, the omega, and the phi, has specific meanings, but your teacher is going to use different symbols in your class, but it's still something in front of x or something in front of t, something added to it, a trig function, sine, cosine, or tangent, and then something out front of it. So if you've never done it before, that's fine. We will have to learn this, though. So my intention is to treat this like you've never seen it before, but I know that you're going to be also getting this reinforced in your pre-calculus class. Now, if you're in calculus, you should have already seen this. However, there are some students who missed this. So if you're falling through the cracks on it, we'll just go through it, okay? It's not particularly hard. And luckily for us, and for those of you who have seen it, we don't have phase shift in what I need you to know. And everybody who's done this will understand why it's nice not to have phase shift. So, all right. I want you to stop for just a minute. Think about, waking up this morning, and consider for a moment all of the things that you know can tell you the time. And in doing this, would you please take out your phone? And if you have a wristwatch, please take it off and place it in such a way on your table where you can't see the time. So face down, clock's facing away from you. Because I know there's no clock in my room. I've purposely taken the clock off the wall. We are interesting creatures, us humans. If we look at what you did in your lab, the idea of the mass on the spring begins here. You might not know why this is an important relationship, but if you look at the roots of this relationship, the part of the relationship that actually matters, so not the 2 pi and not the square root, but the fact that inside here is a simple fraction. The top of that fraction, inertia. The bottom is restoring force. All simple harmonic oscillators do the same thing. They have some force that tries to restore the object back to its equilibrium position. The oscillations are controlled by both inertia and the size of that restoring force. In a spring mass system, it's obvious. The spring applies a force to the object. You can see it there, and you have a stiffer spring, it's going to try and push that object back faster. That's why it's in the denominator. A stronger restoring force makes the object oscillate faster. But if the object has more inertia, it oscillates slower. It's harder for it to move. So guitar strings or strings on a violin, the ones that make lower notes are the heavier strings. They have more inertia. Thus, they oscillate back and forth slower. Look at the size of the mouthpiece between a tuba, a trombone, or a trumpet. The mouthpieces get smaller so that less of the lip will vibrate. Less of the lip vibrates, there's less inertia. Less inertia means it vibrates faster. So the tuba, biggest mouthpiece, lowest notes. Trumpet, smaller mouthpiece, higher notes. Look at all the woodwind instruments. They have a reed, a piece of wood that oscillates back and forth. You can buy reeds that have a higher restoring force and reeds with a lower restoring force, changing the tenor of the note. You apply them under pressure and you use your lips to control the aperture. Those things combine to change the restoring force. You use the entire air column in the instrument as inertia. Plug up more of the holes, you have to force more of the air to move, more inertia, lower note. You guys all had to play the stupid recorder and get your little belts on it. Remember that? Once you pass, hot cross buns, you get a new belt because you've now mastered recorder. You made the low notes by covering up all the holes. You made the higher notes by opening up the holes. Less air moving, higher note. Your voice is no different. You look at the action of the vocal column. The way in which it works is to restrict the motion of the air through the column and reduce how much of the chords actually vibrate. You're manipulating restoring force versus inertia. In all cases, these musical instruments all operate on the same principle. Most all of you have probably had to deal with a string instrument in middle school or elementary school. They force you all to music class once a week and everybody rotated through. You know, tightening the strings of a guitar makes the pitch higher. You're increasing the restoring force, making it oscillate faster. Every system that oscillates operates on the same principle. Whether we're talking about a musical instrument or a building, they're all designed in such a way as to manipulate restoring forces. You want to try something interesting? Talk about simple harmonic motion. All of it is connected to just these two variables. Now, we're going to study it in probably much more boring detail than that, but at least at some point or another, we're likely to be able to apply this to all of the things we just talked about. Now, I need to hit this idea of restoring force first, and I know some of you have already peaked. So yes, I am aware of those of you who looked at your clocks. I can't believe you didn't make it that long, because it hasn't been that long.
Expose me.
No, I don't have to.
No, you just exposed me.
We're not going to be able to go through all of this because I spent too much time setting it up. But I want to start out with the first picture, which is supposed to picture equilibrium. An oscillator doesn't oscillate until energy has been given to the system. So in the case of our current state of the system, it is in equilibrium. And what that means is the net force is equal to 0. The spring is in a relaxed state. It hasn't been displaced. And because it hasn't been displaced, there is no unbalanced force on the mass. This system has no energy. Simple harmonic oscillations begin when the system has been given energy. So if I were to just quickly draw a line, this line represents the persistent location of equilibrium. The first thing I'm going to do is I'm going to set the system into motion by providing some maximum displacement. But I want you to understand one more topic before we actually get to the details. I have to talk about something called restoring force. So, what makes an object a simple harmonic oscillator isn't just that it can be modeled using a sine or a cosine function. What makes it a simple harmonic oscillator is that the sine or cosine is a result of a Hooke's law restoring force. I can't prove this to you because your mathematical skills aren't there yet. But what you don't see pictured here is that this is a second order differential equation, which can only be solved with sine and cosine. Someday you guys will reach a level of mathematics where you'll understand what this means. And actually in mechanics, we'll do the work on it. But there's three simple parts here. And they are, in fact, quite simple. X represents how far you displace an object. So I want you to imagine at the bottom of this bowl, I could place a marble. That would be what we'd call equilibrium. The bottom of the bowl, it would just stay there. If I was to displace the marble up to the side of the bowl, this displacement is X. Would you agree that there will suddenly be a force that's going to exist to try and push the marble back towards equilibrium? The force that exists comes from the curvature of the bowl. Well, that's the K portion here. How curved the bowl is would determine how much force pushes the marble back. If the bowl were more steeply curved, you would probably agree it would push the marble back with more force. And if the bowl were shallower, it would push the marble back with less force. But it's important to understand that this negative sign means that the marble is pushed back from where it came. That's what makes it a restoring force. It's important because without that negative sign, if this were our bowl, so give me a second, but I take the bowl and turn it over, I could place the marble on the top of the bowl here. Again, I have an equilibrium position. If I'm careful to place the marble right there at the very top, the marble will stay there. That's equilibrium. But if I were to displace the marble to here, would there be a force on the marble?
Yes, but not for you.
But is it going to be a force that will push it back towards equilibrium? No, this would be a self-destructing system. I would have a very precarious equilibrium, and any movement away from equilibrium destroys the system because the system falls apart. Believe it or not, that is the difference between having a negative sign and not having a negative sign. This isn't Hooke's law. This won't restore the system to equilibrium. A restoring force will restore a system to equilibrium. A Hooke's law restoring force is directly proportional to displacement. It's important to understand the difference. There are lots of systems that oscillate that aren't Hooke's law oscillators. A Hooke's law oscillator, if I double the displacement, it doubles the force. They are directly proportional. We're going to look at only Hooke's law oscillators. Just so you know, this would be an example of a non-Hooke's law restoring force. Right here. It's a restoring force. There's a negative sign there, but X is to the Q power. So this restoring force would not have the same properties. I would not be able to use this to describe the period of this oscillator because it's not a Hooke's law restoring force. I can't explain all of that to you, but it's critical that you understand this is a direct result of this. Negative sign and everything.